So today we're going to learn about gradient descent, and gradient descent is the thing that lets machine learning algorithms learn. So all the stuff we did up to this point, there was like all of the math, which is like our prerequisite that we need to understand what we're doing. There was last workshop, which was setting up the right equations, figuring out, how do you calculate things. But it's still not the learning parts. It's like okay, we've set up the constraints, we've created the blackboard, we've gotten the chalk, we've gotten ready to learn, but now we're actually gonna learn. So this is exciting. But to get to the point where we're ready to learn, I'm gonna give you a quick recap about what is the goal of this algorithm. And after that, we're just gonna dive into how do we achieve that goal. So to get to the quick recap, let's just talk about the equations we saw last time. So when we're doing machine learning, we're going to have some set of input features, x, and in the last example, they were like, has a user listened to a BTS song in the past week? We're going to have this vector, theta, both of these are vectors. Theta was a set of parameters that we have, parameters as in adjustable variables. So this is very special. This is where all of the learning is going to happen, because the job of the algorithm, remember, is to adjust these parameters theta so that it can get better predictions over time. And better predictions just means more accurate to the labels, more accurate to the correct answer. So when we multiply all the input features with all of their respective parameters, what we're doing is we multiply each individual one, add it all together, we get a weighted inputs. It's kind of like, okay, you take all of the input features and then maybe I multiply one by 10, I multiply another by 1, I multiply another by 0, because that one's not even important. We're giving each of the inputs a relative weight, kind of like a importance. So algorithm pay more attention to this weight versus that weight. Now, the next thing we did was we put the weighted input through a sigmoid function. You don't need to remember the formula. Just know that the sigmoid function takes in whatever numbers you have and compresses them down so they range from 0 to 1. And the reason we do that is because, well, in the example we saw, we were trying to predict, will the user buy a BTS ticket or not? And that's kind of like 1, they will buy, or 0, they won't. So when we put this weighted input into the sigmoid function, inside goes a number, like say 1,000, and outside we get a number, like say 1, because 1,000 is really big. It gets, compressed down to the upper range of the 0 to 1. And that's what we get when we have the activation. Activation is the word we're going to be coming back to later. But for now, just think of it as the weighted input compressed to a 0 to 1 range. When we get to neural networks, then you'll see a more visual way of understanding why it's called the activation. Finally, when we have these activations, remember, they're just like 0.2, 0.8, 0.9. They're just like numbers that are close to either 0 or 1. So for our predictions, we can just round off, the activations, and we're like, okay, the algorithm it predicted 0.8 here. That's close to 1. So technically, we're just going to say that the output is equal to 1. Last equation is the cost. So the cost is how we measure the performance of the algorithm. And the way we do that is we take the difference between here, that's the prediction of the algorithm. Over here, that's the label, that's the correct answer. Ideally, we want the difference to be 0 because we're like the predictions we create with our algorithm, they are equal to the actual correct answers. We just square it here to get rid of any negatives and positive signs, because what we're doing is we're going to add up all of the examples we have. So let's say, the first user, the second user, the third user, and M just means, the total number of examples. And then we divide by m because we're going to add these all up and then take the average. So that's the cost. Hopefully you still remember a little bit of these equations because, well, I explained them extensively last lesson. But these are the four equations that we call feed forward. Feed forward as in you go from the inputs and the parameters and you go all the way forward through all of these equations until you actually get at the cost. That's the output of a machine learning algorithm. So I hope there are no questions up to this point. Review makes sense. So I just want to highlight one specific thing here. When it comes to the cost, remember this. Over here, this is locked. The output, the label, the correct answer is locked. M is locked because you can't change the number of examples you have. The only thing that can change is the prediction of the algorithm, y hat, we call it. Well, y hat, it depends on A depends on Z, and Z depends on X and theta. Well, X is also locked. X is the input. You can't change the input. It's whatever you get. So the only thing that can change is theta, and that will affect the cost. So what's happening here is whatever changes we make to our parameters, they directly influence what the cost is. So if we want to lower the cost, if we want to make our predictions more accurate, what we have to do is we have to change the parameters in such a way that it leads to a lower cost. That's a really key idea to get in mind. These are the settings of the algorithm, and we need to twist the dials, we need to adjust the settings so we get a better output, a better cost. And I can graph this relationship. So if I put the cost on the vertical axis and the parameters that I have data on the horizontal axis, well, what's happening is I know the parameters here, that's a vector, and here, like I'm just putting in random numbers, but this is a simplification. Like imagine you're just taking the average of all the numbers, all of the parameters, and that's what you have here. But if we just, assume, data, that's the input, it has different values, which I understand are vectors, not scalars. If we simplify it down to this case, then it's like, okay, let's say theta is equal to -2. It's going to lead to a certain cost, and the cost is going to be equal to, this value here. When we set theta equal to a different number 3, then it's going to have another cost. And here at 2, notice this point is special. This is the lowest cost that is possible given any input data into this function. So our job is to go from a value of theta like 3 to a value like 2, or a value of theta like -2 to a value of +2. The reason is that when we change the value of theta, then we can minimize the function. That's just a technical way of saying when we change the value of theta, we get a lower cost. Our job is to get the lowest cost. Is this making sense? So I'm going to do something weird here, and I understand it's weird, it's fine. We're going to do something weird just to please me for a little bit. I'm going to focus on this point right here, and I'm going to make a tangent to this point. Remember from, I think, the first lesson, that was like 2 weeks ago, a tangent is just like a line that touches a slope or a curve at one point. So this blue line over here, it touches just this point. It is the tangent of this graph of C over theta at this point. I see you have something in the chat. Somebody's already got it. Okay. So we have this line here. It's the tangent line. of this point, and I want to focus on one particular aspect of this tangent line, which is going to be the slope of the tangent line. You can see the slope is m. Somebody already caught on to what I was doing. So a tangent line is a line at one point, and I'm taking the slope, the rate of change at one point. You guys remember what that is in calculus? Someone humor me. I don't want to listen to myself talk the entire time.
Yeah, derivatives.
Okay, it's the derivative. So the rate of change at one point, it's the derivative. And specifically, the derivative here, it's partial c by partial theta. So how much does a very tiny change in theta affect c? What is the change in c over the change in theta? These are all different ways of saying the derivatives. Now, one thing here, the reason why we put partial c by partial theta instead of just like d c by d theta, it's because if you saw my lesson on partial derivatives, whenever we have a bunch of equations with a bunch of variables, and like we're isolating the effect of one variable here, just theta, then we use the partial symbol because it's like, okay, just focus on theta and let's lock all the other variables so that we don't have to worry about this mess. So that's why I'm using partial. Now, one thing to note here, this slope of a line, it's a line pointing downwards. This slope is negative. And that has an interesting implication because look at the place this point is in relative to the lowest point. Because that's where we want to go, right? We want to go from this point to this point. So this point, it needs to go more to the right. The way that's going to happen is if theta increases. So theta needs to get bigger. If it gets bigger, if it goes more in this direction, then the resulting cost will decrease. So keep in mind that trend for a second. So the derivative we just got at this point, the derivative is negative, and the way we want the slope to change is positive. Let's do the same thing again here for this point. So over here, I'm going to make a tangent line. Tangent line touches at one point, like so-ish. I'm going to make this line purple. All right. That's good enough. It's a tangent. Okay. It's a badly drawn tangent. Now, pay attention here. I'm going to do the same thing. So, rate of change at one point. That is the derivative. And here, I'm going to take the slope again, slope of this purple line. Note, this purple line, it has a positive slope. And again, I want you to note the relationship. So over there, that was negative. Over here, the slope is positive. The derivative at this point was negative. The derivative here is positive. But here we want the theta value to decrease. Because if it decreases, then the point will get closer where we want it to. And you can think of it as that, but technically what we're doing is when we decrease the theta value, then the cost gets lower. Is this making sense? You see the relationship? Derivative here is negative. We want the theta value to go up. Derivative here is positive. We want the theta value to go down. It's like there's an inverse relationship. I shouldn't use that word technically because it's not correct, but you get the idea, you get the message. So here's what I'm going to do, okay? I want to change the theta value so that when the slope is negative, I want the value to get bigger. When the slope is positive, I want the value to get smaller. So here's what I'll do. I'll just take this. Remember, this is the slope. You know, this fancy notation, that just means the slope. If this is negative and I subtract a negative, that means I'm just making theta bigger. And that's what I want. You see? I want to go from -2 to +2. I want to make theta bigger. Over here, I'm doing the same thing, but in this case, the derivative, the slope, is positive. So this time I'm making theta smaller. And that's what I want to do. I want to make theta smaller. So that is the essence of gradient descent. When we have different points like this, where the points are just, different theta values and the cost that we get, because the cost depends on theta, what we can do is we can take the derivative at the points, and if the derivative is negative, we want to increase theta. If the derivative is positive, we want to decrease theta. I'm making you note this just based on patterns and observations, but in one of the past lessons, when it came to the visualization lesson, there is a little link in the description of that recording that explains exactly why this is the case. So for now, I'm hoping that this makes sense, that we can use these derivatives at different points to figure out how do we get towards a lower cost. How do we change the theta parameters so that we get a lower cost? Is this making sense? Any questions so far? Aditya? You're muted.
What if you're looking at a point that's on the little lump in the middle? So slightly to the left. So that's going to be positive, and you're going to want to go to the left.
And
But
this
that's
point's right
not
here?
to the left of the point, of the lump.
Here?
Yeah. So like on like the positive side of the lump. So you would want to go down, right?
Mm-hmm.
So when you go into the little pit on the left, you're going to realize that that's not the lowest point you can achieve. So how would you know there's a better minimum in the little slope?
Yeah, that's a good observation. I'm gonna graph it out so everyone can see. So it could be that, let's say you have a point here, and if you look at the rate of change here, then let's say I use the color yellow and I quickly draw a line. So if I draw the tangent line so that I can get the slope, the tangent's going to look something like this. This tangent has a positive slope. And if you subtract the slope here, then it's going to end up going left. Theta parameter is going to decrease. It's going to actually end up going towards this point. Yeah, that is a correct observation. So you can have what are called local minima, which means if you just look in like this little area, this local area, then the algorithm is minimizing the cost certainly, but it's not getting to the lowest global minima, the lowest point on the graph if you look at the entire graph. Unfortunately, the gradient descent algorithm, it cannot fix this situation in 100% of cases, though we will look at a tool later on that will help us fix the situation a little bit better. Sound good?
Unless it has a lot of GPU power and it graphs out each and every point of the graph to find which one's the lowest.
That's also not possible. We have other methods, but we'll cover them later. when would you use local minimums? So at any point you could have local minimums. Remember, the goal of this algorithm, it is to decrease the cost by adjusting the parameters, by adjusting the theta parameter. And if it just finds a local minimum, well, it's decreased the cost relative to where it started out, so it's doing its job. Obviously, we want it to do a little bit better. We'll look into it a little bit more so that we can develop this algorithm so that it can improve. Yeah, good thinking, guys. Good observations. So this is like a basic version. This is like how you could theoretically do gradient descent, but as uh, as our astute listeners have pointed out, you know, it's not the best. We want to improve this a little bit. So let's look at some implications. One thing I did want to note just before we left this basic version of gradient descent, if you notice this purple line, so the tangent here, the derivative here, it is steeper than this blue line, the tangent, the slope of the tangent, the derivative here. In math words, the absolute value of the second slope is greater than the absolute value of the first slope. That symbol, the bars outside, that just means absolute value. So that means, yes, over here theta is going down, over here theta is going up, but look what we're doing, we're just subtracting the slope. So if this slope is bigger, then that means like maybe you go from 3 and you subtract the slope here, which is bigger, maybe you go down to 2.5. So maybe you go down in this case by 0.5. However, this slope, it is not as big. The magnitude, that's another way of saying the absolute value, that is smaller. So maybe you just increase here by 0.1. Over here you went down by 0.5. Over here you went up by 0.1. So the bigness, the magnitude of the derivative, that does matter. It determines how much does theta go up or down by. Make sense? All right. So now let's try and fix the problem that you guys just noted, which is that what do we do when, say, there are local optima? What do we do when, let's say, the slope here is so big that maybe, maybe the slope is so big that it doesn't go from 3 to 2, it goes from 3 to like 1. What do we do then? Well, let's take a look at a few scenarios. So the first scenario I want to point out here is, let's actually just take a look at what would happen. Let's follow the process through. What would happen if we just used gradient descent, but did it repeatedly? So this basic version, what if we just did that repeatedly? So let's say we started at this point, we want to get to this local optima, and we drew a slope here. Slope was positive, so we did what we're doing, which is theta minus the derivative, and slope is positive, so theta decreases, and let's say it decreases to here. Yeah, then let's repeat that. So we do the same thing, but this time the slope is a little bit less steep, because like over here slope was steeper, over here slope is less steep, the derivative is less big, it has less magnitude. So maybe like here, theta went down by 0.5, maybe here it only goes down by 0.3. And again, slope gets less steep. So maybe here it only goes down by 0.2. And then slope gets less steep. Maybe here it only goes down by, 0.2 again, and 0.1, and like 0.05. And like you make all of these tiny, tiny, tiny little steps. Again, the entire time you're just doing the same thing, theta minus the partial derivative. But it's just getting, the slope is getting smaller and smaller and smaller. So each step is getting like slower and slower and slower and slower. This is taking forever. You know, there's got to be something better we can do, right? Right? Yeah, there's something better. Are you optimistic? That is like the least optimistic optimism I've ever seen. Okay, fine. Do you guys? No optimism today. That's fine. All right. So let's say we're doing this thing over here, and we're just repeatedly, going down, updating the data parameters, and I just want to change the notation up a little bit. Remember, this is like just a storage container full of all of the different data parameters. That's called the gradient vector. I'm just using this symbol because remember, data is in like one scalar. It's not like data is equal to 2. Data is like a bunch of different, parameters. So data 1, data 2, data 3, all the way up to data n, whatever n may be, like data 100. So I just changed this up a little bit, but it's the exact same thing as earlier. It's just taking the partial derivative. It's just taking the uh, the rates of change of the tangents. However, it's just a group of them. So this is what we're currently doing. You're seeing a bunch of issues here. What if it overshoots? What if it's just really slow? What if it finds the global minima instead of, what if it finds the local minima instead of the global minima? Let's try and fix this. The way we're going to try and fix this, here you see another example where you'd have really, 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 really slow updates. So maybe like this one is fine, but then the next few are getting slower. A way to fix this is we could try and artificially mess with the magnitude of the derivative we're getting. So make sure that the derivative is at least like a certain amount so big. We could do that by using another parameter. We're going to call this parameter the learning rate. It's the Greek letter alpha. You might also see it written in courses or textbooks as the Greek letter eta. Eta. It looks a little bit like an N, but overhang here. So these different things just mean the learning rate. Why is it called the learning rate? Because remember, when the algorithm is learning, what it's doing is it's changing the data parameters. How is it going to change the data parameters? Well, it's going to calculate these derivatives. Remember, this is just another notation for saying all of the partial derivatives of data, because data is just not one scalar. And we could like adjust this parameter. So let's say like you have a really, shallow graph here. It's not very steep. Maybe you don't want to set data, maybe you don't want to set alpha, the learning rate, to 0.1. Maybe you want to set it to 10. Over here, on the other hand, like let's say you have a steeper slope. Okay, maybe we don't want to set alpha to 10. Maybe we want to just set alpha to 0.1. And why are we setting alpha? Well, it's just increasing the size of the derivative, right? Like if alpha is set to 1,000, then we're gonna take all the slopes we get, multiply them by 1,000. So it's not like theta minus, 0.5, it's theta minus 0.5 times 1,000. So theta minus 500. The values are gonna increase a lot faster. The algorithm is gonna learn a lot faster. Is that making sense? Arjun, no? Would you like me to try re-explaining that?
Yeah, once more.
All right.
Just
So,
the learning rate thing.
so before, we were just taking theta and subtracting the derivatives we were getting. So let's say we calculated m at this point, and m is equal to, it's equal to like 0.5. Yeah? Well, then we could have like, theta is equal to 5 minus 0.5. And you just have like a change of 0.5. Because that the entire change, the rate of change, is dependent on this value right here. However, if we introduce like a well, let me explain that word later, but let me say if we introduce the learning rate and we set this to a really large number, like, 1,000, then this is going to get a lot bigger. It's not just going to be, subtract away 0.5, it's going to be subtract away 0.5 times 1,000. And we'd want to do that, if we have a shallow graph like this and like the slopes we're getting are always really small. So instead of having like these slow updates, this one, then this one, then this one, then this one, the rate of learning of the algorithm gets larger because, we might get larger jumps. We go from here to here to here to here, and eventually we make our way more quickly to the lowest value. Aditya?
So what might overshooting mean?
Overshooting might be that, let's say you set the rate to 1,000, the learning rate, alpha to 1,000. In this case, it wouldn't make sense because like, let's say 3, you wanted to go down by 1, and you set the rate to 1,000, then, you might end up somewhere over here. Like you don't want that. So you have to choose, it's called a hyperparameter. So remember the theta, that's a parameter because the model is updating it. Hyperparameters are ones that we have to choose. That's where we have to put in the right judgment. So if we choose the wrong hyperparameter, then we can overshoot our value. That's the word you used, overshoot. So we can maybe go from like 3 all the way to -2, whereas we only maybe wanted to go from 3 to maybe 2.5. So theta, it can change more quickly or more slowly, depending on how do we set this hyperparameter, alpha or eta, but in general called the learning rates. Making sense?
Is there some equation to find out the hyperparameter? Or is it just like through experimentation?
Oftentimes at the beginning, it's just going to be through experimentation. Later on, we'll look at other ways. Sounds good? So we have figured out the conceptual basis of gradient descent. This is it, okay? Not too hard, right? You just repeat this equation a bunch of times until you get from the initial point to the next, to the next, to the next, to the next, until you get to the optima you want. Or you could just say, okay, repeat this like 450 times and that's it. After 450 times, then we're good. Don't need to worry about it anymore. So in any case, that is gradient descent. Not too bad. Just gotta understand this concept, you can subtract the derivative at a point so that you can get theta to the value you want. Not too bad, could be worse. However, we have this large mystery. How do we get this thing? How do we get that partial derivative? And here, I'm just gonna say this notation is just because theta is a vector. If that notation is confusing you, remember, it's saying the exact same thing as this. What is the partial of c by theta? This would be like the way of saying it if there were just one theta parameter instead of a whole vector of them. So in any case, how do we get these things? The way we do that is a very famous or infamous, I'd rather say infamous based on my prior experiences with this. We do that with an algorithm called back propagation, which is very infamous. And if you go on YouTube, it's very irritatingly confusing. However, I think I've explained it pretty simply here. Back propagation just means don't stop using the chain rule ever. Ever. Never stop using the chain rule. That's all you do. Just use the chain rule. So if you don't remember how back propagation works, that's just it. It's just using the chain rule. Also, I keep using this word algorithm. I didn't define it earlier, but it's just a general concept in computer science for a repeatable set of instructions so that you can achieve some goal. Here, back propagation, it's like a repeatable set of instructions so that we can figure out what these values are. Yeah, making sense? You wanna dive into it? No, that's fine. We're still gonna dive into it. So here, as a restatement, you see all of these equations? When we're trying to find the partial of C by theta, what we're really saying is, let's say, theta has some value. It's a knob, it's a setting. We give it some tiny nudge in this direction. What happens to C? How does C change with a tiny nudge in theta? Now, this is a little bit complicated because, we don't just have theta here that we can directly see, how does this connect? In the middle, we have all of these different knobs and levers that we can turn. So, you know, theta changes a little bit. That changes the weighted input, Z. And then Z changes a little bit. That changes the activation, A. And then the activation changes a little bit. That changes the prediction, Y hat. And then Y hat changes a little bit. And then that finally changes the cost. So we have all of these layers of abstraction. Uh, these are all just values on a number line. And the last one over here. So this is going to change. That's going to create like a domino effect. It's going to create a chain reaction. Hey, chain reaction, chain rule. Well, guess what we're going to do? So we want to figure out partial C by partial theta, which means tiny change here. How does that affect here? The way to do that is we gotta work our way backwards through all of these changes. We gotta figure out, okay, so we have a bunch of changes. How much does C change with the change in Y hat? How much does Y hat change with the change in the activation? How much does the activation change with the change in the input? We're just going our way backwards across all of these changes till we get to the beginning. And look how we do it. The chain rule. Remember this thing? We can break down partial C by partial theta into, this first change. Yeah, this change, what change here? And the second one, and the third one, and the fourth one, all the way until we get back to theta. And remember the algebra here? This cancels out with this cancels out with this cancels out with this. Eventually, you just end up back at partial C by partial theta. It's like they're being multiplied, right? Just like fractions. Is this making sense? Let me see the chats. Change into, yeah. So here you'll see what the change ends up being. So what does a change in the rounding of the activation? How much does that actually change? Conceptually, it's like still a change, but you'll see in a second that it's not a big change. Any questions so far? Do you get this concept that we're using the chain rule to get back through all the changes, back propagate through all the changes so that we can figure out, okay, if this changes and we work through all the layers, then what's going to happen at the end? I see a bunch of silent faces. I don't know if that means you understand. Hopefully. All right. I'll assume no questions means you do understand. So in the end, that is it. That is backpropagation. That is what we have to calculate. And each of these terms, so partial C by partial y hat, partial y hat by partial a, all of these terms, we can calculate the derivative. And we can do that using the rules that I explained in the calculus lessons. So if you remember those rules, go ahead, try what these calculations are You can literally calculate them yourselves, but I'm gonna do it for you for a second. So if we work through all the derivatives, what we end up getting is this first thing is equal to 2y hats. This one is equal to 1. This one is equal to a complicated thing. So this, remember, this is like how much is there a change in the sigmoid function? I know this looks weird. I will link to a description that shows like a derivation of the sigmoid function. And finally, this is partial z by partial theta. You can, again, always go back and try the derivations yourself. One thing, just a small thing to notice before I get to the questions. Over here, the cost is being sum across all of the examples. And here what I noted was I noted the derivatives for each example. So at the end here, we're just gonna sum across all of these values. So put a big group of square brackets here. And so for each example, we're gonna calculate these expressions. And remember, y hats, that is a value we have saved. We got the algorithm's predictions using this formula. And same thing for the x's. We have those values saved. So that's why we can compute these things. And we're just gonna sum them over all of the examples. So let me quickly write that and then I'll come to the questions. Copy that and here. So that is it. That's back propagation. It is hard to pronounce. It is, I think, explained badly sometimes, but in the end, it's just the chain rule. Never stop taking the chain rule. Now, let me quickly get to the questions. But since y hat is a rounding function, yeah, so first question, since y hat is a rounding function, is there no change in the activation? That's exactly why over here, the derivative is kind of like 1, because like how much does a change in this activation value affect y hat? It kind of doesn't really. It's like a one-to-one relationship. If, the activation is 0.99 and then y hat is like about 1, it doesn't really change that much. And it's not like a directional change in any case. So that's why this derivative ends up being 1. It's just like a rounded version. I can, hopefully that makes sense, that concept. It's not really changing, you're just like rounding a few numbers here and there. And see the next question, why back propagates? So here, again, back propagation is an algorithm. Algorithm is a repeatable set of instructions to achieve a task. The task here is we're trying to calculate these values. So this is like the notation for a single number. So theta is equal to 2. But this is the notation for all of the vectors. So theta 1, theta 2, theta 3. Why are we trying to calculate this? Because in gradient descent, we need to calculate this value to figure out how much do we change the theta parameter. Why are we trying to change the theta parameter? Because when we change the theta parameter, say from, theta is equal to -5 to theta is equal to +5, then we can lower the cost. Because the cost, as you see here, remember what I explained at the beginning, x is locked, y hat is based on just theta, and then y hat is the only thing that changes in this function. M is locked, the label y is locked, x is locked. So the only thing that can change is theta, and that, as a result, changes the cost. So hopefully that makes sense. We're trying to change theta so that we can minimize the cost. We change theta with this equation, which uses the partial derivatives. This is just the gradient, which is a group of partial derivatives. And the partial derivative is computed with back propagation. That's why we need this algorithm. And this is the thing that you need to understand. This is just like derivations. I'll link to some YouTube videos, and you can try these yourself if you want to figure out, hey, how do we derive these equations? I think there was one last question in the chat. Let me take a look. Doesn't it also save time to do back propagation? Sierra, do you want to explain this question just to make sure I understand what you mean?
Like it was like something you were explaining earlier when you were like had the visual of like changing like the like going from like for example like -5 to like 5. You were mentioning how you like take like tiny steps. So I thought like that back propagation made that a little faster, or it made like made the increments bigger.
Yeah, so that's actually the learning rate, this hyperparameter. So back propagation gets like a number for you to put in here. So for example, you get a number like 0.5. And then let's say like 0.5 is too small, then alpha or eta, the learning rate, then you can multiply it by, let's say 1,000,000. You wouldn't do that, but you could try. Then you could multiply that, so then this is bigger, and theta decreases by a larger amount. Remember what's going on here. Theta is like subtracting a number at the end of the day. So this is how much theta is going to change. So the steps, the size of those steps, that's why this is called the learning rate. It's controlled by the hyperparameter alpha, eta, whereas backpropagation supplies this term. It supplies the value to fill in here. Is this making sense? Arjun, Aris? All right, so it looks like there are no more questions here. That is basically the lesson. One thing to keep in mind, you might not see like graphs like I did them over here. There's just C on one axis, theta on the other. You might see 3D graphs, which are like, okay, one axis here, that's like theta 1, over here is theta 2, and then up here is the cost. And, they're doing gradient descent, and they talk about, ball rolling down a hill. Turns out it doesn't matter which of these pictures you use, they're both incorrect. Because like there's not just, two, it's not just like you have theta 1 and theta 2. You have like theta 3, theta 4, theta 1,000. So you can't visualize that. And over here, like as I said, I just assumed that theta, it's just like one number, like theta 1. And that's also not correct, because there's thousands of theta variables. So these are both just like visualizations, they're just approximations. The real truth is how gradients actually work, and that was explained in the visualization. If you look in that recording, there's like a link in the description that explains why this is true. But it doesn't matter, we're just visualizing, what's happening, and what's happening is we're changing the theta values so that we decrease the cost.